Good evening, Berlin, and welcome to the Science Slam of the Berlin Excellence Clusters. Hello, everybody. It's so good to see you again. After a year, I missed you. Why are we here? Well, to celebrate science. This is the 6th day of the Berlin Science Week. Who here in the audience has already visited some other events of the Berlin Science Week? Yeah, that's the spirit. The rest of you, good luck, there are 4 days left. Yeah? So, uncountable number of events in Berlin celebrating science in different formats, and of course the slam is the best. So what are we here for? We celebrate the young PhD students and young postdocs from all the 7 Berlin clusters of excellence. Now first let me tell you which clusters. In the alphabetical order. Contestations of the liberal script. Math Plus, Matters of Activity, NeuroCure, Science of Intelligence, Temporal Communities, and Unifying Systems and Catalysis. Now, who here in the audience has never heard the name Clusters of Excellence before? Okay. Okay, so let me introduce you to the concept. The idea basically is that researchers from different institutions and different universities, but from the same area, in this case Berlin-Brandenburg, share forces and raise funds together to fund their work. So, not all from the same university, but basically working on similar projects, from math to literature research. That's a cluster of excellence. Right? And 270 people in a rocker club celebrating them, that's a science slam. Now, who here in the audience has never been to a science slam before? Well, then I guess I have to introduce you to the concept. The slam is defined by 4 rules. There are people on stage who present their own research in an understandable way, entertainingly, and in less than 6 minutes. Okay? So that's where you come into play. Because the time rule is really crucial. For a simple reason, if you don't give a scientist a time limit, they just don't stop talking. And now in the first row, I need people who maybe have a time counting device or are able to count to 6 and want to have a beer. Yeah. What's your name?
Jade.
Big applause for Jay. Lessa, kannst du mir bitte mal ein Bier bringen? Ein Bier bitte. Okay. Jay, you have a very important job to do, right? This is meet the Zeitschwein. The Zeitschwein will tell the slammers, first of all, when 5 minutes are over, so that they know, oh God, I have to hurry up. Means whenever a slammer starts, you take time, and after 5 minutes, you give a little hint. And then after 6 minutes, when time is over, you can be a bit more aggressive. Okay? Want to try if this works? Yeah? Awesome. Big applause for Jay. Now, in case Jay didn't reach to the slammers, or in case something went totally wrong and they keep on talking, then something weird will happen. That means that I will come on stage and slowly come closer. Until it gets really uncomfortable. Yeah? And if they still don't keep on talking after 7 minutes, we just cut off the volume. And then the slam has come to an end, no matter what. Okay? Yeah. We do this in 10 rounds, 10 slammers today. And after the end, you guys have another important job. All of you. You have to decide who's going to be the winner of today. Because there will be fabulous prizes. And we don't have so many, so we have to find out a winner. And there's a quite easy way for you to choose. Just be emotional, right? So we do this by clapping, and there is a quite simple 10-stage applause system. Now, applause level number 1 is really, we won't hear this, but this would be like, huh, what? So, how would a stage 1 applause sound like tonight? Yeah, that's terrible. Stop. We won't hear this anyway. Stage 5 applause is like, yeah, okay, yeah. What would a stage 5 applause sound like tonight? 6, 7, 8, 9. Okay, stop. You got it. Stage 10 is yay, is yippee, is eureka. And how would a stage 10 applause sound like tonight? Yeah! Exactly, you definitely got it. Now continue like that, because here are the slammers of tonight. Anushka Ghosh, Katarina Krivokuća, Laura Untner, Lesa Yurtseva, Marwa Zainelabdeen, Raza Weber, Tamana Ahmad, Vito Mengers, Yang Fan Peng, and Yuna Kim. Okay, so we're all set, right? We can start. No, we can't, because we have to find out the order in which these guys will present. Now, please take one of these little Zettelchen. Das waren 2. And since I'm a well-prepared host, of course, I made them big enough so that all of the audience, even in the back row, can see them. Yeah. There we are. Und jetzt, show me the number. 7. Anushka is 7. Katarina, number 1. Laura is die 4. Lesa, number 8. Marwa, number 2. Raza, number 10. Tamana, number 3. Vito is 5. Young Fun is 6. And Yuna is number 9. Okay. Stand once, please, in the order of appearance. Now, who's number 1? Katarina, I guess? Yeah. Number 2? Where's number 2? Please, stand here. Number 3? Number 4? 5? 6? Where's 7? 8, 9, 10. So, remember that. That's the order of appearance. 1, 2, 3, 4, 5. After you, there will be a break. And then you have like 15, 20 minutes to empty the bar. Then we have the second round, and afterwards we're gonna choose the winner of today. Thank you, guys. All of you can disappear except for Katarina. Big applause for the slammers of tonight, please. So, und jetzt, wer ist Katarina? Wer ist Katarina? Where is Katarina? Ready? Yeah? Okay, Katarina Krivokuća, right, is a mathematician doing her PhD at the Freie University, Berlin, with the Excellence Cluster Math Plus. She loves exploring patterns and structures, and after her talk, you may too. The title of her talk is We Got Everything Covered. And the 6 minutes are gone. The stage is yours. Big applause for Katarina Krivokuća.
Hello. So I've been looking for an apartment in Berlin. And since that's really depressing, I'm thinking about how I decorate it. I like patterns, as Jochen said. So I like to have these little dots on my floor. And these will play a role now. This is my favorite carpet in the world, okay? And I want to take this carpet, and I have loads of them. I put one here, centered again in this dot. I put another one, and now brace yourselves. I put a shitload. Okay, great, I've covered my floor. But if my carpet had been a tiny bit smaller, we would have been in problem because now not all the floor is covered and the floor is lava. That's really illegal. So great, my favorite carpet was exactly the correct dimensions. We go back to my favorite carpet, not a smaller version. Okay, and now I notice that some of the things here are kind of too carpeted. Okay, like these orange triangles here, I've covered them kind of a lot of times, and I don't want that. I want to conserve my carpet. Carpet is expensive. So I take this little chunk, and I'm also myself bad at crafty things, so I only know how to make straight cuts. I see that I can make this straight cut to cut off this top. Boom, I cut it off. But whoo, this new version of my carpet still covers everything. So again, I've cut this off in every one of these carpets. Okay, but now I can also do the same with the lower chunk, chomp, and the other one, chomp. And I have a new little hexagonal carpet. Ooh. And it still covers everything. But as you can see, now nothing intersects any of the others. And these did not have to be carpets from the beginning. These could have been tiles, for all I know, because we don't need to cover things on top of each other like here. Okay. Phew. I have my carpet in my imaginary flat that I still don't have. Now, next problem, Wi-Fi. I want to do the same funky thing with the Wi-Fi. And again, I don't like boring shapes of Wi-Fi signal. So this is currently my favorite Wi-Fi router emission. This is how far away it goes. This is exactly the shape I want. And I want to do the same process all over again, as I did with the carpet. Make it as small as possible so it still covers everything, and then try to chop things off. Okay? And chop, chop, chop. Great. The thing is, this is already perfect. I chose my favorite Wi-Fi router as we cannot chop anything off. If I make these Wi-Fi routers in a grid, this will perfectly cover everything and I cannot chomp anything. But if I put two on top of each other, the same thing doesn't happen as with the carpets, because you see this red part here? They overlap. They overlap in such a weird way that whichever corner I try to chomp off, I will have a dead spot in my apartment, which is not what we want. So, as we can see with the carpets, we had a nice situation where whenever we want to do the game that I play, make something as small as possible, then chop, chop, chop. I always get a tile. In 3 dimensions, I already don't have to get something that could have been plastic or metal or whatever. It has to have a way of intersecting itself. But yeah, here I have some intersection. And sadly, in my apartment, I don't have anything 4-dimensional to show you. But in 4 dimensions, we're not even sure if these shapes need to be flat. These are very, very weird beasts that we don't fully understand, but can happen in our everyday life if we have funky Wi-Fi routers. So now I have my carpets, I have my Wi-Fi, I only need an apartment, so I go back to Wege gesucht. That's about it from me. Thanks.
Schnipp, schnipp. Here. Okay, thank you, Katarina. Now, the next speaker of today is Marwa Zainelabdeen. She's also a mathematician, also a PhD student at the Freie University with Excellence Cluster Math Plus. Her passion is about running simulations and comparing them with mathematical theory. And here is why. That's the choreographer of nature. Big applause for Marwa Zainelabdeen.
Hello everyone, I'm Marwa Zainelabdeen, and thanks God we're going to get rid of mathematicians in the beginning of the slam. So I'm going to tell you about the choreographer of nature. Who is he or she? Where is your next flight going? Did you book it? Well, just all in one voice. I'm going to... Exactly. So now, traveling time for flight has came. Please fasten your seat belt. Jet is about to take off. You are now 11 kilometers above the ground, sipping your 9 euros coffee, where suddenly, pump! Your coffee is splashing. The wings are shaking around. And you are there feeling what? How did you feel? Did this happen to you before? Yeah. What actually is going on out there? The captain is announcing turbulence. Few years ago, I would feel terrified. But since I am a third-year PhD, I would rather get excited now. Well, apart from my depression issues, I would get excited because I know that the airplane is dancing now. It's dancing with the clouds. The air molecules are just deciding to have a dance. They're not blamed. We all like some sort of a dance or the other. Who doesn't like to watch a perfect dance? Well, apart from being mind-blowingly beautiful, which is not our interest here, you might have observed that every one of the dancers knows exactly when to move, how to move, and how fast. Did you watch it? Were you watching? So that you have this rhythm among the choreographer. You have a choreography. Now I need imagination a bit. Imagine that you are not watching only 30 girls, but trillions of them in a space. Oh my God, that's heaven itself. And everyone is following exact steps, and there is a choreographer behind. So every girl is actually a molecule. And the choreography that you will be watching is a very natural phenomena. Water flow. What you see here in water flow is an ultimate choreography of dancers synchronizing together. And who is the choreographer of this dance? Who designed it? Actually, mathematicians 200 years ago figured this out. Set of equations, of course, we are math. Wait, who on earth tattoos equations? If not for a pathetic, absurd math PhD student. Well, I'm not gonna explain the equations for you, but they're called Navier-Stokes. And I don't want you to hear the guys. They are gone already 50 years ago. But if you are interested, you can come to the bar, and I'm going to show you my tattoo. Why did I tattoo them? Why did everyone tattoo them? It's because when you have solution for this, you will know how each and every molecule around the Earth will fly and how fast and with which pressure. Exciting. Do you know what that means? It means we will know how the water in the Pacific will move around from now and forever. Every single molecule of air and gas. We will predict everything forever. But bad news, equations are not solved. Actually, if you solve them, you got $1 million in cash and retire. This is not what I'm planning to do. But if the equations are not solved, how are we doing these things? I mean, we are flying and everything. And here comes the essence of our research. I am a very tiny piece of a moving wheel who are sitting on the computers the whole day. That's all what we do. And teaching the computers how to dance. This is all what we do. Navieri stocks are coding in the background, and we represent every year molecule with an arrow, and these arrows are dancing with a very nice rhythm, exactly like the girls. Different scenarios are happening. Whether the scenario is with the water, or the scenario is a gas, or your blood is beating. And this is all what we do. We are mimicking choreography. So welcome to the world of simulation. Thank you.
So sorry. Thank you. Thank you, Marwa. The third speaker of today is not a mathematician. She's a physical chemist, and she does her PhD at the Freie University with the excellence cluster Unifying Systems and Catalysis, or UniSysCat. She said she would have liked to become a photographer, but as a physical chemist, she's also taking photographs in a way, just in a bit different way. So please, with a warm welcome and applause, welcome Tamana Manju Ahmad with her presentation, Vibral Spectroscopy, Watching Molecules Dance. Big applause.
Cause we don't need permission to dance.
Come on, everybody, let's dance. Perfect. So, just now we talked about choreography of nature. Now, here, I'm going to talk about how to make molecule dance, and not alone, but with you guys. But I will come to that in a minute. First, ChatGPT. How many of you guys are using this tool? Impressive number. So, on one or other occasion, I think several of you have been using ChatGPT to get answers of your question. And like you guys, I also have got a lot of questions in my PhD life. Every day. I'm tired of it anyways. But unlike you guys, I cannot go on ChatGPT and type a big paragraph, hey ChatGPT, can you give me answers of so-and-so questions? It's a bit more complicated than ChatGPT could answer. But what should I do then? Quit my research? Actually, I don't have that option. So I have to come up with answers by doing a lot of experimentations, and for that, I need my own tools, and the tool which I have is vibrational spectroscopy. Ooh. But why specifically this technique? So I will tell you guys in a second, but before that, I want you guys to introduce you with this one. It's a metalloenzyme. Just before starting the slam, one of the slammer asked me, what are enzymes? So here you go, you have the answer. Suppose you want to travel from Berlin to Vienna. What could be the option? You can take a Deutsche Bahn. I see the answer. Too long. So we skip that. So there is an alternate option. You can take a plane. And within the span of 2 hours, you are in Vienna chilling. Woohoo! So exactly like that, these metalloenzymes, they make a reaction, a process very, very fast. And this guy here, it has got its name. We scientists, we call them hydrogenases, and they do the breaking of dihydrogen molecule. And this happens here, which has a cluster of different molecules. But why do we want to study it? Actually, this reaction, when it happens, when the dihydrogen molecule breaks, it releases a lot of energy, and we researchers, we have this crazy idea, or maybe stupid idea, I don't know, that these have a potential of solving future energy crisis, and that's why it's important to study this guy. But the problem is, this guy is very, very sensitive, and it can crash anytime, like sometimes planes crash. But I have got a backup in the form of my vibrational spectroscopy, because it prevents from this guy to crash, keep it intact so that I can do a lot of experimentations to get my answers. And this is how my techniques look like. It also has got its name called resonance Raman spectroscopy. Heavy, I'm sorry for that, skip the name. Just let's focus about the technique. So it has got different lasers, and these lasers illuminate the metalloenzyme to probe the vibrations. Well, by now you have heard this term vibration quite a lot, so now I reveal. Vibrations of molecule. Actually, right now we are here, we are surrounded by a lot of molecules. From the oxygen we are breathing to CO2 we exhale. All of these molecules are actually always in vibrating motions, and they have got their specific moves. Do you want to see it? Perfect, then I show you now. So it can do something like this. Or something like this. Or like this. Cool. And now I will also show you how the molecules in the cluster are doing. Like this, you see? Or like this. And now, we will do a short experiment together. So all the women in the house, give me a cheer. Now all the men in the house, give me a cheer. So now I will bring a slide with a red color, yellow, no, blue, yes. This is correct. Blue color with some music, and I ask all the women in the house to show me their dance moves. You can also use the dance moves of the molecule. And then there comes a red slide, and I want all the men in the house to do the same. Are you ready? Perfect.
'Cause we don't need permission to
Come on.
dance. No, we don't need permission to dance. 'Cause we
Come on.
don't need permission to dance. No, we don't need permission to dance.
Perfect. And when you danced, actually, we recorded this and this. It's called spectrum. And all the signals here, they have got information about how the molecule is vibrating. And then I get to know how this molecule looks like and how it's doing the catalysis of dihydrogen breaking. And that was all about the science of making molecule dance. And now, let's dance together with the molecules around us. Come on.
Don't need permission to dance. No, we don't need permission to dance.
Thank you. Yeah, come on, this is the slam of the clusters of excellence, so I think they can cope with some pressure, right? Anyway, we are already at stage number 4. No, slammer number 4, Laura Undner. She is a digital literary scholar and a literature mediator. Sorry, I have to read that. Currently doing her PhD at the Freie Universität with the cluster Temporal Communities. She just loves gossip, but only if it's a few hundred years old. So the title of her talk is The Ancient Greek Poet Who Broke My Computer. Big round of applause for Laura Undner.
Hi. Yeah, maybe a quick question to begin with. Who here tends to overthink things? Raise your hand so I can see you. Yes, my people. Nice to meet you. I am one of you. Now, next question. Who here tends to overthink ancient Greek poetry? Yeah, I thought so, but that's why I'm here. I'm a digital literary scholar, which means I work somewhere between literature and computer science. And my mission is quite simple. I want to teach computers to understand literature so that we can capture, in a machine-readable way, how literary texts talk to each other. Because if we can teach them to follow how stories respond to each other, we might understand things about how they do that we didn't know before, and store that knowledge in a really sustainable way. And to do that, one day I thought, why not just make my computer overthink the topic like I do? And I did, and my computer did not appreciate it, which brings us to Sappho, my test subject. Sappho lived around 600 BCE. She wrote about love, heartbreak, longing, basically the Taylor Swift of antiquity. But most of her work is lost now. We only have fragments left, many just ending mid-sentence, like I want to say, and then silence. And yet she never disappeared. Writers kept bringing her back, quoting her, rewriting her, imagining her life again and again. In a way, literature never stopped talking about Sappho. And that's what I wanted to capture. How do literary texts about Sappho talk to each other and to Sappho's own work across centuries? You know, each author picks up a line, twists it, adds a comment, and passes it on. To me, that's basically gossip, just an older, nerdier version that probably never ends. And I needed my computer to understand this gossip so that it could capture the knowledge I wanted to explore. One example. In 1818, Austrian playwright Franz Grillparzer wrote a tragedy called Sappho. It's about the famous poet Sappho, who's adored by the world, except by the man she loves. He leaves her, she despairs, and she jumps off a cliff. Just 1 year later, in 1819, a writer named Adolf von Schaden published a play called The Modern Sappho. He took Grillparzer's tragedy and turned it into a parody. He used the same names, motives, and topics from Sappho's work, but twisted them to make fun of the play. So, in a way, Sappho inspired Grillparzer, but Schaden wrote a parody about his play, and Schaden probably read Sappho himself too. That's literary gossip in full action. So, I asked my computer, can you follow that trail for me? Can you find where authors quote or copy or twist each other? And the computer said, I am happy to assist you, but I will need data. So I gave it data. I marked in each text, this is a quote, this is a character, this is a motive, just 300 texts with those little markings. And this got me over 400,000 triples. That's over 400,000 tiny statements of literary gossip. And yeah, that's when my computer finally broke. And I'm not kidding, I really need a new computer because it's simply too much data to process. See, computers don't gossip like humans do. They gossip in triples. Subject, predicate, object. Like Sappho inspired Grillparzer. Grillparzer was parodied by Schaden. Each triple is a small fact, but put them together and you get a network, a machine-readable reconstruction of how literary texts talk to each other. But, of course, being an overthinker, I made it a little bit more complicated. And I used a model that doesn't even allow me to say the word text anymore. In fact, I added 4 extra layers to every text: work, expression, manifestation, and item. So instead of saying things like, this text quotes that text, I said things like, the expression of this work quotes the manifestation of that work in this item. It's like Russian dolls. It makes me happy because it's so precise, but it makes the computer cry because it has to add so much data going through the layers all the time. But it's powerful. The computer can now see on a very detailed level how literary texts talk to each other, from the simple idea identified by the work to the specific book you have at home, the item. Now, people sometimes ask, can't AI just do that? Well, no, not really. AI is great at guessing. If you give it, I want to say, it will finish the sentence, but it doesn't know where that line came from or who reused it 2,000 years later. My approach, so-called semantic modeling, is different. It doesn't guess, but structures knowledge. It doesn't make things up. It only connects what's really there, so the result is a reliable, machine-readable history of literary gossip and a friendly reminder, don't overthink just by yourself. Let the computer do it with you. Thank you.
Thank you. Laura Untner. Okay, guys, it's already the last slam of the first half. And this role will be played by Vito Mengers. He holds a master in computer engineering, and he's currently doing his PhD at Technical University with a cluster Science of Intelligence. Working at the intersection of robotics, perception, and computational knowledge of intelligence, he asks himself, why is my robot still stupid? A big applause for Vito Mengers.
Hi, thank you. I know it was an amazing performance coming down the stairs, and I know it's hard. Why do I know? Because I'm a roboticist, and we know doing things in the real world is hard. Because, you know, even the expensive robots, very expensive robot, they struggle, they're a bit stupid. I mean, look at him. And once things go bad, they go worse, and worse. It's pretty tough being a robot. And it's even tougher being a roboticist, because nowadays I'm getting asked, so when will AI make this disappear and robots good? Well, you know, fantasy worlds like the internet, AI got you covered. But will it really take over the physical world? I don't think so. If you're really afraid, just leave your door like slightly ajar, and I think the robot won't come to get you. It will fall down at the door. And this is really weird, right? Because we humans, we're crazy good at this stuff. Physical world, we got it covered. And it's not just us. This is a kakadu. And now we'll try to open like a very complicated physical lock because there's a cashier behind. And I mean, look at it. There's screws, there's like a wheel, there's a ledge. It's doing all of it. Like, it can do it. No robot can do that well. And it does it all with a fucking beak. We have very expensive robot hands, and they're not as good. So that's weird, right? Why is that? Well, you might say we are just not very good at our job. We're like actually bad at programming. And might be true, I don't know, all of us. Nah. But, I think there's an additional issue at least, which is that we don't really understand how we humans do it. For decades now, people have thought that we're doing something along the lines of first sense, like how is the world around us, then make a very complicated plan to achieve our objectives, every step down the stair, whatever, and then just execute it. Easy enough, right? Problem is, the world is kind of messy, and these plans usually don't work out. Or in the words of John Lennon, life is what happens when you're busy making other plans, because, the world is a mess. So what can we do instead? Well, I would like to suggest to just, instead of planning 100 steps ahead, just let's try to get the next one right. Just one. Essentially, react your way through problems. So let's see how that looks like when we do that on a robot. So meet my robot. This is my robot. It's a cute little arm. It has a hand up there, a camera below the hand. Actually has a very expensive force sensor in the wrist. These things are 10K just for one sensor. It's a bit crazy. And it doesn't know a lot about the world it is in. It just knows there are drawers. Drawers are supposed to be open. So it will try to open it. And otherwise, essentially, it will just react to how things change when it moves around the world. So if we now look at it moving, what we'll see is that it will try to figure out where the drawer is, essentially just by triangulating. All of this just reacting, one step at a time. 30 steps a second, but reacting. And then you can feel how the drawer feels like, open it. Yeah, thank you. But it gets better if you just react, because if you just react, actually, if there's weird stuff going on in the world, like me, oops, spoilers, no. But these videos aren't playing. Well, let's react to that. So as you can see, when weird stuff happens in the world, like me coming up to the robot trying to make it fail, it actually can figure out how to resolve that issue. It just reacts to how the world actually is and how it actually develops. There's no plan. And in the end, you will manage and open the drawer. And you've now seen it already. This is not just, kind of nice. I think for us it's a bit simple because we as humans are very good at this stuff. But for robots, Olympic level performance, you can win big awards with it. Just, Thank you. An award for opening a drawers. My parents were also elated, just like you guys. But the question is really, what do we really learn from this? And we learn one thing from this, how to build better robots, not by planning, but by reacting better. But if we're really honest, we're also learning something maybe about how we do things. Because I think if all of you are honest too, we are not very good at doing stuff really according to plan. Stuff goes bad. You've seen humans do bad things. And really, the trick is just to know how to react to them. And I hope with this, I give you a lesson for your life. Maybe just plan less, react more. Thank you for your attention.
Vito Mengas. Thank you, guys. So this was the first round. I guess you have a bit to discuss, maybe a bit to drink. So that's what the bar is for. Meet in 15 minutes. Enjoy your pause. See you again soon. Hello, everybody. Hello, Berlin. Are you still there? No, you're not there. Are you still there? That's the spirit. Okay, I kindly ask the people in the first row to stand up because there will be thousands of people coming in now and it might be a bit eng. Thank you. We heard 5 motivated young slammers in the first half. Now be surprised, there are 5 more up there who would like to share their enthusiasm about the most beautiful thing in the world with you, science. That's what we'll, exactly. Now, the first speaker of the second half is Dr. Yang Fan Peng. He is a trained medic. Yeah, not yet. He's a trained medic with an MD in neurophysiology. And he leads the research group at the Neuroscience Research Center of the Charité, and he's affiliated with the Excellence Cluster NeuroCure. He's so fascinated by synaptic microcircuits that he even thinks about it when playing football. That's why his title of his talk is Football Tactics in the Brain. Now, with a hysteric applause, is the time ready? Wonderful. With a hysteric applause, Yang Fan Peng.
Hello everyone. So I study how neuronal networks in the brain process information. And in order to tell that, I first have to introduce some very basic and fundamental principles of football. So, it's a sport where we have 11 players on the field that pass the ball to each other to score a goal. And the way they pass this ball and combine these passes, or tactics, greatly determines how well the team can perform. And this is basically how the brain works, more or less. So, what you can see here, what the brain does is it has many different brain regions. Each one has its specialized function. And here you see an area that can process language. And a lot of that processing actually takes part in the so-called cortical areas, or the most outer layer of the brain. And if we zoom further into it, you'll see a lot of densely packed cells, nerve cells, or how we call them, neurons. And these neurons communicate to each other, and they're connected via these structures which we call synapses. And so you can imagine a neuron's like a football player, and the passes they play to each other are these synapses, and they are connected through them. And just like with football tactics, actually the way the ball is passed around, or the neurons are connected to each other and communicate, greatly determines the way it can perform information as a network. So, most of these studies previously have focused on the cortex and connectivity in mouse brains, and not much is actually known on the human brain. So I set out to understand the football tactics of the brain of the human. So how do we actually measure connections in the brain? Let's go back to football. Now imagine you want to understand the tactics of your opponent. Now what you could do is you could actually sneak into their practice, and then you play the ball to one of their players, and then you observe to whom does he play the ball next. And then you do this repeatedly, quite often, and not only to one player, but maybe also to the other players. And then you try to take statistic and account for how frequently are the different pathways being played. And then you might get a rough idea on the tactics of that team. So basically that's what we did in the lab. Now, first we got human brain tissue from the surgical theater. This has to be removed due to medical reasons, and normally it's just been discarded, but thanks to the consent of the patients, we're able to use that for our scientific project. So we take a slide of a brain, put it under microscope so we can see the different neurons. Then we can use these tiny micromanipulators, or tiny robot hands, to move a very small and fine glass pipette through the tissue to poke these neurons. So this is one neuron. And if we have poked it, this technique is called patch clamp, then we can record the electrical activity of each neuron and also stimulate it, as shown here. And we can then, just like in the undercover practice operation, get each of these neurons to be active or fire, and then see how do the other neurons respond to that. And because our setup allows us to record up to 10 neurons at the same time, we can really understand what the network structure of this network is like. And so what did we find? So first of all, imagine you're Toni Kroos. Now, if you have the ball, you play the ball to, so for those who don't know, it's a German midfield player, and you play that ball to Rüdiger in the defense. But he plays the ball back to you, and you play it back again, so it goes back and forth, and the commentator says, Kroos, Rüdiger, and so on. gets quite boring after a while. I mean, they might improve their accuracy in passing, but the game does not really leave their field, so it does not lead to much. Similarly, it has been previously described, this is a network structure of the mouse cortex, where different neurons are very reciprocally connected to each other, so they connect back and forth. And this helps to amplify always the same kind of information, but not much more complex stuff. Now imagine Toni Kroos, instead of playing back and forth, plays the ball forward to Gündogan, he then places to Havertz, he gives the ball to Musiala, and then he scores a goal, right? 2-0, that's a reenactment against Scotland last year. Now, basically very something similar we also found in the human cortex. So here you can see an actually experimentally recorded cluster of neurons, and this is how they're connected to each other. And you can see that the connections are very feed-forward. There are no reciprocal connections there. Now this really allows this neuron to be more independent from each other, and the whole network to store more information. So to functionally test this hypothesis, we also simulated artificial neural networks, some that look more like a rodent brain, some that are randomly generated, and some that more are like these human data we just looked at. And in fact, we really saw that when we gave this AI network a speech recognition task, it's those feed-forward human-like networks that performed best. So taken together, our study could find specific distinct network principles in the human cortex, and we also have shown that these allow a much better computation. And maybe, who knows, one thing, these feed-forward network structures, very interesting that they are also observed and used in nowadays modern AI networks. And who knows, maybe one day our national team has to play against the FIFA AI team. So thank you all for your attention.
Yang Fan Peng, thank you. Danke. The seventh slammer of today is called Anushka Ghosh. She holds a master in biotechnology and is currently PhD student at the Humboldt University with a cluster unifying systems and catalysis. If you don't find her nose deep in some fantasy novels, she's busy in working, well, easy problems, reducing the CO2 in our atmosphere. The title of her talk is Who Let the Heems Out? Big applause for Anushka Ghosh.
Hello everybody, my name is Anushka and today I'm going to talk about puppies. I wish. No. I'm going to talk about hemes and heme proteins. But before I get into the scientific nitty-gritties of it, I want to take you on a journey with me to the future. The year is 2100. Little Thomas has to go to school. He gets up in the morning and sees the sun streaming through his windows. He looks at the watch. It's 6 a.m. in the morning, and it's already 6 degrees outside. Thomas sighs to himself, puts on his protective suit, and gets ready to go to school. Does it sound a bit like science fiction? The truth is, unless we do something about it, it is not going to be science fiction. Now, that was a heavy story. So, collectively, everyone, I want everybody to take a deep breath. Yes. That breath that you just took carried in oxygen through your bloodstream, and it was carried by these little guys called red blood cells. In particular, the heme protein inside your red blood cells called hemoglobin. You might have heard of it. The hemoglobin has this molecule called the heme molecule. It's absolutely fantastic. It has an iron in the center. For people who are anemic, this is the iron you guys are missing. Okay. So this iron in the center, it not just carries gases, it can also change gases and break them down to be something else, which is what I wanted to do. I work with another heme protein, not hemoglobin, right? And this guy I can make in bacteria, which makes it very cheap and easy to produce in large quantities. And I can also produce it in the presence of oxygen, which you'll have to trust me on this is a big deal for the kind of reactions we want it to do. On top of all that, it's also really big and strong and super stable. So the goal with this is to make it do CO2 reduction. Now, before I explain how I really go about this, which of us have a rich grandma? Okay, not me. No one? Oh God, okay. Well, imagine you have a rich grandma, and a rich grandma gave you this house, okay? The house is really beautiful. From outside, the surroundings are so pretty, the walls are really nice. But once you go inside, the furniture is kind of old, the curtains are backdated, the house kind of smells, you know. But what you can do to the house is you can renovate it. Renovate it to suit your needs, which is, of course, to throw a party, right? This is exactly what I do also with my protein and with my project. I have this heme protein, which, like I said, has the iron heme in the center. But there are other hemes which have different other metals in the center. For example, copper, nickel, cobalt, zinc, magnesium, manganese, right? And these are the different other hemes with different metals that I introduce inside my protein. Now, I can't just do that and expect it to work, right? I also have to see how did it work, right? For that, what I do is, and I also cannot trust my protein, like, yeah, I know you changed. Okay, right, like you said the last time. So what I do instead is I force them to become protein crystals. You heard that right. Just like salt crystals, sugar crystals, proteins can also form crystals. Yay! And when they form crystals, I bombard them with X-ray, just X-ray, okay? And once I do that, what happens is I can get an image of the protein, which I can later study. Here's me, hard at work in the lab. What? No. Here is me, hard at work in the lab, okay? Trying to study this picture. Once I can understand how the changes have taken place, I can also focus on the reactions it is doing and try to understand what products it is changing the CO2 into. Because at the end of the day, the goal is to say goodbye to carbon dioxide. The reason I do this research, the reason so many of us do similar research, is because we all have this one big picture to look forward to. A day when Thomas can take off his suit and breathe in peace. Thank you for your attention.
Anushka Ghosh. Okay, so for the next slammer, we have to prepare a little thing. Wait a second. Anfassen oder wo machen wir das? Okay, you haven't seen him. Nothing happened. The next slammer is called Lesa Jurtsever. He holds a master in history and musicology and music training or something like that. And he's now doing his doctorate with the cluster Contestations of the Liberal Script, or just scripts. He says music and academia have always gone hand in hand in his life. Now let's hear more about that. Do, re, mi, fa, sol, how to compose liberal music. Lesa Jurtsever.
Don't start the timer. Thank you. So, as a pianist, I performed on several stages. And I remember one time an elderly German gentleman, I think like 80 years old, approached me and said something I will never forget. He said, "That was such a nice concert, but I didn't expect someone with dark hair and a thick beard to play Beethoven." And I was like, "Come on, dude. What did you expect? Belly dancing? Me riding a camel? Oriental music? Tarkan's Kiss Kiss?" So tonight I want to test a bigger idea, which is also the key question of my PhD project. Can music change how we see a person? Can music change how we see a larger audience? Or can music change how we see a nation state? In my PhD project, I'm looking at Turkish composers going to the United States and presenting Turkey as a modern and liberal nation. And what I found out is that they use different kinds of musical genres to present Turkey in different kinds of fashion. And tonight I'm going to look at avant-garde music and liberalism. But just a quick historical background. After World War II, Turkey wanted to join the new liberal world order with the US as a key ally. It joined NATO, it joined the United Nations, and Turkey joined even the Korean War in 1950. And the US saw Turkey's geopolitical potential against the Soviet Union. So both governments wanted to improve relations, but there was one catch. US audiences still thought of Turkey as a mystical place far away with hook-nosed barbarians possessing harems. And they thought Turkish music would sound like this. So, how do you challenge these kind of stereotypes to improve relations? Well, Turkish composers worked together with the Rockefeller Foundation. The Rockefeller Foundation invited Turkish composers to go to the United States and perform at several venues, such as the New York Public Library. And Turkish composers could present their newest musical art, avant-garde music. I know, it doesn't seem pretty. But actually, that's the core idea. It doesn't want to be pretty, and it doesn't want to tell you a heroic story. It doesn't want to tell you a love story. It doesn't want to please you. It doesn't want to evoke emotions. It wants to be liberal. But what does that mean, liberal music? I will share with you 3 key ideas of liberal music, and maybe those of you who are composers or musicians can take this as a short guide to compose this kind of music. So first, liberate the music. What does that mean? Forget about old musical habits. The rhythm goes on vacation, melody doesn't text back, your ears do Pilates, and your face discovers muscles it didn't know before. Second, challenge your listeners. See them as individuals, self-determined individuals, not as masses. Address them and provoke them. Do not try to please them, but challenge them. And third, talk to your audience. Ask them what they think about your music. What is their reaction? Did they have any stereotypes or not? And in the case of my Turkish composers, they had a clear message. Forget about the harem postcard. Meet the new Turkish liberal elite and embrace Turkey as a modern state. Now you might ask, did it work? Did it work? Did they change perceptions? Yes and no. So people listening to this kind of music are maybe elites, intellectuals, but not the masses. So maybe someone heard these Turkish composers and told their friends or their family members about the Turk composing the newest innovation in classical music. And what about our guy from the beginning, the German gentleman? I don't know if I changed any of his stereotypes. But what matters is that he met someone who played something that he couldn't know can coexist. And this is where change begins. Thank you very much.
Lisa Yutseve. Okay. And now I would kindly ask all my slammers to come down on stage. In the order of appearance, Katarina Krivokuća. Number 2 was Marwa Zainelabdeen. Tamana Ahmad, Laura Undner, Vito Mengers, Yang Van Peng, Anushka Ghosh, Lisa Yutseve, Jona Kim und Rasa Weber. Now, who here in the audience is old enough to remember the German TV show Herzblatt? You know who Susi was? Yeah? Anyway, maybe that's the wrong joke. I'm too old. Sorry. Since the first talk may be a bit long ago for your brains at a later stage of that evening, I try to recapitulate this, the content in one sentence. And I will ask the slammers to go one step before, and when I say who will be the slammer, or do you think this will be the slammer of tonight, and then I made this, and then you clap as crazy as possible. Remember the 1 to 10 stage system? What a 10 stage was like? 10 stage? Exactly. So, remember, think that Katarina Krivokuća getting Wi-Fi signals in her apartment using carpets would be the winner of today, then please applaud now. Thank you. Or do you think that Marwa Zainelabdeen, dancing with clouds, men, women, and fluids, and all molecules in the universe, should be the winner of the day? Then please applaud now. Thank you. Or Tamana Ahmad. She has the permission to dance with her metalloenzymes. Do you think she's going to be the winner of today? Then please applaud now. Thank you. Or do you think that Clemens at the technical board in the back doing the technology for us today should be the winner of today? Then please go crazy now. Laura Undner teaches her computer not to cringe on ancient Greek poetry. Do you think she should be the winner? Then applaud now. Nummer 5, wer war Nummer 5? Vito Mengers. He reacts his way through the problem of opening drawers. Do you think he should win? Then please go crazy now. This will be close. Yang Van Peng. He plays football with neurons reciprocally for computation. Please, when you think he should win, applaud now. Thank you. 777. Anushka Ghosh. She lets the hymns out to reduce the O2. Or Lisa Yotzever plays the piano. You need to let me finish my sentence. Yuna Kim, not now. You can step forward, but not them. She studies Hamburg on many levels to give life and doesn't make sense to care for each other. Anyway, you think she should win? Applaud now. Or last but not least, where is she? Rasa Weber dives to let corals grow and restore coastal life. Please, now. Okay, wait a second. I sent the data to the computer. Yeah, we got a result and it's close. And I think it's not eindeutig. We have to go to make a Stechen. I see close result for Anushka, Lisa, Rasa. Yeah. And what we now do is that you guys have to decide on one. And yeah, sorry guys, you have to choose the winner of today. And I give you a time limit. Whenever my arm is lifted up, you go crazy, but only for these 2 seconds. And it's only on volume, okay? Anushka? Stop! Guys, only when my arm is up. Lisa? We really have to train this with the signals, but anyway. Or Rasa. I'm not so sure here. Let's do this again. Rasa? Lisa? Anushka? Anushka Ghosh is the slammer of the night! Congratulations! And of course, we will not let the people go home without a big thank you to everybody who worked in here. A big applause for Lucas on the board, for Clemens who did the technical, Eric and Henning for the camera, all the slammers tonight, of course, for you for being here, and for the Roadrunners Paradise to be the greatest club in the world. One last word before I give them the presents. I would like to announce one more show, just one. I said there were 4 more days on the Science Slam, yeah? On the Brain Awareness Week. No, that's in March. Berlin Science Week, goodness. On Monday, the last day of the Berlin Science Week, we all meet again in the Fahimi bar at Cottbusser Tor. Because then there will be also from the clusters of excellence a pub quiz. And then you can show what you learned. So see you again on Monday in the Fahimi bar. But now, let's give me the presents. Number 1, this is for you, Anushka. Number 2, number 2, thank you. Number 3, also that's, thank you very much. All of them will get vouchers because PhD students like to read. And that's why we send you all to the Dussmann to get a voucher. And you'll all get, apart from the free beers tonight, some more giveaways from the excellence clusters. Now go crazy for the slammers. Stay here, drink more, talk to them, ask them out, and enjoy the rest of the evening. Thank you very much. See you on Monday. Thank you.